So the next method, smoothing. Here we're not removing points, simplifying the line. This is, I suppose, in some respects similar, you might think, in the sense that sudden changes in direction are going to be removed. But this is actually changing the geometry of the lines. We're going to, rather than just move in straight lines between these nodes, we're going to try and represent the journey, as it were, around this line using some function, so that we can describe all of this more in a mathematical sense, rather than just a change of location or coordinate. We have a mathematical description, and that allows us to move more smoothly through this line. It reduces a lot of the noise, as it were, without perhaps losing too much detail. This is obviously going to fail under some circumstances where you have lots of changes in direction close to each other, and you can end up with some very strange looking functions. So this has to be used with caution, and it's not always a great idea, but we can use it to remove some of the, as it says, the angularity of the lines, make things look more smooth, which is often more pleasing, but also sometimes it will help us to interpret the map, and symbols don't get confused with each other. We can follow the direction more easily and separate them out from each other more easily with these smoother lines. So moving on from the previous two were focused mostly on lines. It's not just for lines. Polygons consist of lines, let's not forget that. But we can now start talking about just a more generalized form, where we aggregate a number of objects into something else, something that is in an area object, into a polygon. So we've gone from saying that there are these houses here, these 7 houses, and we say, well, instead of there being 7 houses, there's just a residential area. We don't want to have these 7 houses all mapped out. It's it's not going to work in our new map. The scale is going to be wrong. So we'll just say, here are some houses. This is an area containing houses. This is a residential area. We'll draw it as a polygon. It's a much simpler geometry, less information to store, and we don't have all of the details of these houses to worry about creating noise on the map. So we've made the decision to say that this is no longer a group of houses. It is another one thing instead, that is an area object. How do we do this? Because obviously the forms can be quite complex. So if we start off with this collection of buildings that we have here, we can then perform a Delaunay triangulation on the geometry of these points. Delaunay triangulation you have come across without knowing it perhaps when we introduced the idea of the triangulated irregular network, which is what this resembles, the tin. In our first GIS course they were mentioned, but we didn't really look at them. They're coming in more and more now, and you are using them on this course. And what we have here is we've used the method. Normally this is used to represent, or often this is used to represent topography, for example. But in this case, all we're interested in is the sort of bounding line, the outer boundary that can most easily be found around these objects. Can be found by a computer. Well, how is a computer going to do this for us? And so we use this concept of Delaunay triangulation to create this tin, triangulated irregular network. It's Delaunay triangulation of the point data, the nodes in these polygons, and then we set a threshold for the maximum length of a line on the outside edge of this area. It's an interesting concept. So we can see that the basic triangulation within these objects, or sort of between them, we've got this sort of break-dancing Scooby-Doo figure here. And then we've increased that to sort of generalize away even more details. We set this maximum length for the sides, and we say anything longer than that outside of these lengths, they go. We're not interested in them. And so we end up with this delineation of the area, this line that represents this collection of houses. This is our new area object rather than these building symbols. So that's how we simplify this. We collect all these objects down into to one new type of object. We aggregate them into something else. So using this Delaunay triangulation. So just a quick explanation of what Delaunay triangulation is. It's a tool used, as I've mentioned, in several different ways, but to create, say, triangulated irregular networks, amongst other things, but Delaunay nets as well. So here we have a very simple, there's just 4 points here, and Delaunay triangulation says that the circumcircle of any triangle must not contain any other point. It can only contain the 3 points that make up the triangle it is a circumcircle of. What does that mean? Well, if we look at this circle here, this is the circumcircle of this triangle, and unfortunately it contains another point. This is not Delaunay triangulation. This is just triangulation. And similarly, when we look at this collection of 3 points here that make up this other triangle, this one also contains a point that is not part of the circumcircle. Whereas if we then instead change our triangles, so these triangles, well, there's one there and one there, if instead, using exactly the same points, we triangulate the other way, so that we use these 3 points and then these 3 points, we can see that the two circles, they go through and contain only those points that are part of the circle and nothing else. And therefore this is a valid Delaunay triangulation, which is something we are seeking in these models. We can, instead of doing something, we can apply a similar concept, something called amalgamation, where we take 2 parts or 3 parts or multiple parts of an object and just sort of push them together into one thing. Get rid of the gaps in between. We're saying that generally in this area, well, it's all this green thing, whatever, it's woodland, whatever that is. Okay, and if we're at a scale that's close enough, we can see that there is a gap between them. But when we step back, as it were, well, it's just that this whole area is basically woodland. If this is woodland, so we amalgamate those two into one larger polygon, just to get rid of the unnecessary details. We generalize away these gaps. So that's amalgamation. Fairly simple. We tend to try to at least use the outer boundaries of the object, the existing objects, and just bind them together across here. Remove and keep the external edges, remove the internal edges, as it were, so they become one object. And that we can get something similar to that in a raster format as well. We can do amalgamation when we remove, when we do a kernel analysis and we remove, we go by the mode rather than the average. We look at the mode and see what's the most common existing class within that, and that gets rid of the minor classes in a particular kernel, and then move the kernel over and do the same thing again, and get rid of some of the noise, as it were, the smaller details. Another thing we can do is classification. We reclass the data. In this left-hand version of the map, we have 3 types of, we have 3 classes of thing. If this is a field of wheat, and this is a coniferous forest, and that's a deciduous forest. And then in our new map, we say, well, that's just a field, and that's forest. We don't care what type of forest it is, it's just forest. So we've reclassed it into 2 different classes. So that also removes the need for this boundary, simplifies the data down to fewer types of things. So we classify the object, reclassify it into something else. It's another form of generalization. Another interesting one, selection. This is performed. Let's just move on to the example. We have areas where there's lots of things happening, and maybe that's fine when we are at a scale where we can see all of these objects distinctly. But if we're at a different scale, see here, it starts to get quite noisy in the map, and it can be difficult to see where all of these boundaries are, what's actually happening there, distinguish between the different objects. This is a phenomenon we're going to look at in a minute. So instead, what we do is we remove some of what we consider to be superfluous details. We try to hold on to the important points so that we maintain the impression. So, for example, the outer boundaries of where we have buildings have been maintained. We've also tried to keep in some of the key buildings, the distribution throughout, to show there's a reasonably even distribution, and perhaps being opposite this road was of interest as well. Certain key elements are playing in here to determine which objects we're going to keep. But generally speaking, maintaining the distribution, the range and distribution of the objects, so that we get an idea, a general idea. Select away the things that are just filling up the space and not adding to the general impression at this particular scale when we've zoomed out, as it were. We can also try something called a collapse. This doesn't remove things, but it removes some of the detail. So if we take the right-hand example, we essentially have with the detail that we've lost when we go from this broad. Let's say this is a road, and we represent the road with a broad, a thicker line symbol, where we have the white line in the middle and two bounding black lines. But if we simplify that down to just representing roads as single lines, if these were representative of, say, road width, perhaps we've lost that information there. Maybe we can maintain it by using different lines here as well. But we've just collapsed that down so the symbol itself takes up less space on the paper. Just instead of needing two lines to represent, or essentially three lines at least, to represent each road, we've just reduced it down to one simple black line. Similarly here, we can take this polygon and say, well, we know there's an object there, we're not terribly interested in its shape, we'll collapse it down to a point, a symbol, a point symbol. What that point symbol is, it can vary, but we'll collapse it down to a single point. Here we've collapsed the thickness of this line down to a single line. Whereas here we've actually changed the nature of the object. This could also be polygons that we're collapsing down to lines, representing them in that way, but it might also just be changing the symbol so that they become thinner. How is this done? I mean, this can be an interesting problem, because we have a polygon. Where are we going to place the point? Well, if we have a nice polygon like this, we can draw a bounding box around it, and then we take the center of that bounding box and we put the point there. And so that's that central point there, this bounding box around this object, we'll put the point there. That's straightforward, easy enough to do. So that we've done there. But what happens if our polygon looks like this? It's got this sort of hole cut into it. And we put a bounding box around it, and the center of the bounding box isn't actually within the object we're interested in. So if we were to put our point there, our point symbol to represent this object, it would be where it isn't. It would be very specifically in the wrong place, you could say. And that's definitely one interpretation you could make. So how do you get around this? I mean, obviously you want the symbol to be within the object it's supposed to represent. I mean, it is within it in a certain sense here, but I mean, let's imagine we got rid of that. It'd be an even harder argument to make. So how do we do this? Well, commonly there's something called point on surface, where we draw a line through the thing that we want to represent. We take this line going through the middle, halfway along the bounding box, and then we travel along that line, and we say, I've entered the object, I've exited the object. I've entered the object, I've exited the object. However many times that occurs, and then we look for the biggest of these sections, and then we say, right, I'm going to put the point symbol there. So then we've placed out our point symbol for this object within the object itself that we're initially supposed to be, or the initial shape of the object that we want to represent with our new point object. You could argue that this seems to bias the positioning strongly over here, and why not down here? Or, how do we get this right? This is a very difficult question. It will be a compromise. It's always going to be wrong, but this is approximately a good idea. So that's now become our new point there. The exact positioning, something similar that we can consider here, where the symbol, the object being represented by a particular symbol isn't where the symbol is. This can be a problem, but it's quite often necessary to do. And this illustration shows us what's happening. We have a line symbol, say a road, and then this line follows the true geometry of the road, say. And then we've placed out our point symbols for these two houses with the node, their insert nodes, on the center of where the houses actually are. So we followed the coordinates correctly. And then we have, say, the boundary of woodland behind here. The problem we've got is that our point symbols to represent the houses are much larger, they're necessarily larger than the house that they represent. In order for them to be seen on the map and function on the map, they must become larger so that they function, so that we can actually perceive them. And that means that we end up with these houses overlapping this edge up here in the forest, that's not good, and overlapping onto the road. So what we have to do is shift things around a bit. Nothing ends up in its true position. We've moved the houses a little bit away from the forest and moved the forest edge a little bit so that it doesn't come down as far. And we've moved the road over slightly so that now the effect, when we look at this map, is that the road passes by, doesn't actually run through the houses, it actually passes in front of them a bit. The problem is that if you were to take your ruler, measure on the map and say, well, where is this house? How far is it? How far is the house from the road? You're not going to know, because in order to make the map legible and nice looking, all of these symbols have been sort of shifted around a bit so that they become clear and distinct on the map, and therefore they don't truly represent the actual position of the objects. You can never rely on it being entirely accurate. There's always this problem of the little lie in a map, and lots of these little lies all across the map, and we have to remember this and work with them. So we have to be very careful how we interpret the information given on the map. This is something that has to be done for the map to be readable, for it to actually be of use, but the reader has to be aware of these problems. You, as the cartographer, have to be aware of this method and what problems it can introduce for the reader. Is this something you really can do? Is this going to actually present a whole lot of other problems for the person using the map? Who is going to be reading your map? Would this be a problem for them, or is this good enough? They don't actually need that level of accuracy. It's better that they have the general impression. Considerations for you to take. And this we can see not just in this house example, but we can also see it in plenty of other cases. For example, when we have roads and railways running close to each other by rivers and so on and so forth, all different sections and parts of roads. And it looks, if you try and put everything in their correct position, it looks a bit weird and messy, as if the roads are colliding and going into each other. But what's important here is to understand that we have these objects passing alongside each other with a little bit of distance. We're not going to be using this for planning, for building a new road. We want a much better map than that. We need to really zoom in close to see the details. But for the purpose of navigation, well, this is actually more than good enough. Much better than this thing. So this is this idea of displacement. So those were the main methods of generalization that we can look at. What do we do, and why, and what problems can they introduce? In the next section, we'll look at what's behind some of these problems and the very human part of this issue.